actually apply this function to a specific problem. And so here I'm using the auto data from the ISLR package, and I'm fitting a linear model to predict miles per gallon from horsepower. And so that's what this model is here. I can pull out my y-hat values by using the fitted function, and I can pull out my residuals by using the residuals function. And so now I've got my model, my y-hat, and my e, my residuals, and auto is my data set. So if I ran the inside of that function one time, I could set my seed and run that inside, and I end up with an intercept of 38.999 and a slope or a beta 1 coefficient of negative 0.1506. Just to show you that this is working exactly the same, if I set that same seed and I use that bootstrap underscore residual function that I just created, and I plug in the same E, Y hat model in auto, so E is my residual, Y hat is my fitted values, model is my model, and auto is my data, I get the exact same answer here. So when I run that bootstrap residual function, I get the exact same answer when I set a specific seed as I would if I just ran the inside of that. But when I run subsequent calls of this bootstrap residual, instead of having to rewrite all of this code every time, I can just run bootstrap residual again with the exact same arguments, and I'll get slightly different answers. So the second time I run it, my bootstrap coefficient for the intercept is 40, and my bootstrap coefficient for beta hat 1 is negative 0.1597723, which is slightly different than it was that first time. And again, when I run it a third time, I end up with a slightly different result again. So every time I run this, I end up with a slightly different result, which is exactly what we want because we're trying to sort of get a distribution across these different coefficients. Okay, so instead of having to run this, if we wanted to do this, for example, 100 times or 1,000 times, we've definitely saved some time by being able to not have to write this whole thing, all of this, and in fact, we'd have to give everything new names every time. So basically, instead of having to run this 100 times, we could just run this bootstrap underscore residual 100 times. And so that definitely saves some lines of code. It basically saves 3 lines of code for every run. But it's still cumbersome to have to write out bootstrap underscore residual, all of the arguments 100 times. And so that's where the purr package comes in. And so purr is a package for iterating in R. And the functions that we're going to use are all of the form map something. And so this is what it means. You map over .x, and the function you apply to that is .f. And so what this means is for every element of .x, do .f. So here's an example. I've called the purr library, and I'm going to map the numbers 1 to 5, and the function I'm going to apply to those is I'd like to multiply .x, and so that's going to be the 1 to 5, by 2. And so the first element, it takes the first element from this first argument, which is 1, and it multiplies it by 2, so I get 2. And then the second element, it takes the second element of 1 to 5, which is going to be 2, and multiplies 2 by 2. And then the next is 3. 3 by 2 is 6. 4 by 2 is 8. 5 by 2, 5 times 2 is 10. So it applies the function that I put as the second argument to each element of the first function. And by default, this output is going to be a list. But you can actually dictate your desired output by specifying this XXX part of map underscore XXX. So for example, if I wanted to output a numeric or a double vector, I would use map underscore DBL, and I'd end up like this. And so I get the same values, 2, 4, 6, 8, 10, but now it's a vector, a numeric vector instead of a list. And so that's because I use this map underscore DBL. And so here are all of the different potential ones that you could use. So the default for just a plain map is to be a list. Map underscore double outputs a double. And you can try to guess what each of these other pieces are. We've got map underscore int, LGL, CHR, and DF. So int is going to output an integer, LGL a logical vector, CHR a character vector, and DF a data frame. So applying this back to our original problem, I want to run this bootstrap 1,000 times, and so I'm going to set b equal to 1,000. And so I'm going to map from 1 to 1,000, and then the function I'm going to apply is this bootstrap residual, and then I'm going to give all of the arguments that I need for this. And so the e, y hat model, and auto. And so what this is going to do is it's going to run this function 1,000 times. And so you'll see you get this nice list where you end up with the intercept and the beta hat 1 for each of these 1,000 runs. So this is a list as the output, which is the default because I'm using the map function. How do you think I can get these into a data frame? Yeah, so I'm just going to swap out, instead of using map, I can use map underscore df, and now I've got this nice tidy data frame. The first column are my beta coefficients from my bootstrapped intercept, and my second column are the beta coefficients from the bootstrapped beta hat 1. This is great because now we can do something with this data frame to basically analyze or try to estimate the uncertainty in these different parameters. So I want you to use the function that you created in the previous application exercise, and I want you to run a bootstrap on the following model. I want you to use the MT-CARS dataset, and I want you to fit a model predicting miles per gallon from weight and the CYL variable, so from these two variables. And try doing at least 100 bootstraps, or if you'd like to try to do 1,000, you can do that too.